Okay, I think we're ready to go. Welcome everybody to the webcast today. Today we will talk about exoskeletons, reducing joint and muscle loads while performing difficult tasks. So my name is Amir Al-Munajjed. I work for 3 years now at Anybody Technology, mostly on orthopedic and ergonomic models. I'm joined here by Moonki Jung. He's our exoskeleton expert, and also Arne Kies is next to me. He's the host of the event today. So you should see on your screen or behind a little orange arrow a question box, and while I will be talking and giving these presentations, you can enter your questions in there, and Moonki and Arne will try to answer your questions during my presentations, or maybe I will answer some of those questions live after my presentations. So you can enter your questions during the whole presentation. So to the topic today, we have quite some new people in the audience that are new to Anybody, so we'll explain short who is Anybody and what is Anybody. Then we will focus on exoskeletons, first rough giving a definition of exoskeletons, and then I will show how musculoskeletal simulations, especially with Anybody, so Anybody simulations can help during the process of developing and evaluating exoskeletons. And then I will show an example of exoskeletons that how you can do a musculoskeletal simulation to evaluate and develop exoskeletons to reduce knee and hip loads. And I will give basically an overview on what are the important points in there, so how to import an exoskeleton, how to connect it to the human, and what results are available. And at the end, we will have a question and answer panel. So enter your questions, and we will try to answer all of them during this presentations or afterward. So first about who is Anybody. So Anybody there's a company, Anybody Technology, with headquarters in Aalborg, Denmark, and also an office in Boston, in Massachusetts. Anybody Technology develops and provides the software Anybody modeling system, and also licenses, training, support, and maintenance of that systems. And we also do consulting projects with the Anybody modeling system. On the other hand, there's a research group, the Anybody Research Group, based in Aalborg, Denmark, from Aalborg University around Professor Rasmussen, which focuses on academic research projects regarding biomechanics, ergonomics, sports, and automotive. And we also have other affiliated, or Anybody affiliated research groups, one in the US around Professor Petrella, and the other one in Germany in Regensburg with Professor Dehndorfer. So now, what is Anybody exactly? So we usually divide it into the software, the Anybody modeling system, abbreviation therefore is usually AMS. And then with the software itself, there comes an Anybody managed model repository. So that's what we call the AMMR. So this is a repository with many models in there. On one hand, there's a full body model that you can choose from, or several body models in there that you can choose from, and there's a library of applications, of activities. So if you combine both of them, so load a model in the Anybody modeling system, you can perform a musculoskeletal simulation. And then, so basically, if you use the body model and use an activity or motion as input, you can do a musculoskeletal simulation with output like muscle forces, activities, powers, joint forces, or interaction forces to any devices. So this process is called inverse dynamics. So that means input is always motion for our simulations, and output is forces inside the human body or in interaction with some devices. So mostly output is muscle forces or muscle activation and joint reaction forces. So what loads are, for example, in a knee joint or an ankle joint. Here in both of those animations, you see on the left side, you see from a recorded gait lab, like the motion recorded with the markers, and then in the middle, you see in this animation the forces applied, all forces acting on the tibia during such a gait cycle. On the right side, you see the full body model and also some details like a very advanced foot model, or how sophisticated the model is in the lumbar spine or in the hip or in the shoulder region. So the Anybody modeling system is used in various areas. If you start here at the top, from product development or design optimization over ergonomics on the right, surgical planning, or then in combination with finite element simulations, and also as a gait application using AnyGait. So basic or a standard workflow is just analyze an activity in the Anybody modeling system to compute muscle forces, muscle activations, joint forces, but you can do also advanced workflows where you include patient-specific bone geometries from CT or MRI scans, so you don't use the standard bones or the standard body model that comes with the model repository, so you can make your own patient-specific or subject-specific model, or you can also export all the loads into finite element softwares like ANSYS or Abacus. There's also the option here on the right side, you see, to add a scripting hook, like a Python hook, to do advanced mathematical models with Python on top or aside next to Anybody. Or if you have a CAD model, there's also an interface from SolidWorks to Anybody. So if you have a design of an environment or of a device, you can import that into Anybody from SolidWorks very easily. So now enough about Anybody, the Anybody modeling system itself. Now let's focus on exoskeletons. If you like blockbuster movies like I do, you will think exoskeletons are something from the future, some science fiction movies or something. And but that is actually not true. Exoskeletons are used already, or many of them are close of being used in several areas. So an exoskeleton itself is a wearable robot attached to the human body to influence or assist human motion. You can divide thereby, it's either motion assistance for patients in rehab that don't have the full strength, or it can be for people who have their full strength a muscular enhancement, for example for industrial workers or soldiers that need additional strength. So exoskeleton can either have an active engine to provide active torque or force for joints, or it can have a passive stiffness to support or to limit some body motion. So I have prepared a couple of examples, so that is not directly related to Anybody now, but a very famous and very good exoskeleton in the rehab area is the ReWalk exoskeleton that is used for patients with no or low functionalities in the extremities, especially in the lower extremities. So if you have stroke patients, for example, or paraplegic patients, they can learn to walk again with such an exoskeleton. On the other hand, there's if you need additional strength, there are other exoskeletons, like one developed from Honda, or HAL 5 from Cyberdyne. It's also a very famous one. So you can lift heavy loads or perform very difficult tasks without getting fatigued or tired. So keep your joint reaction forces low and still lift heavy loads, and don't have excessive muscle activations while you do difficult tasks. This is also very important in the military area. So also the US Army has, of course, several approaches to use exoskeletons to support their soldiers with a better endurance, to carry heavy loads, their heavy equipment, and to cover long distances by foot. So these are just some examples. So now let's switch to musculoskeletal simulations with anybody and exoskeletons. So basically there are two main areas how anybody can be used, or anybody simulation can be used to help the development process of an exoskeleton. First is to really, during the development process, find optimal parameters of the exoskeletons. So which torque is necessary to perform this motion, or which power is necessary for the exoskeleton. Also, are the kinematics matching with the kinematics of the human? Are there any stiffnesses like springs in the systems? So you can find out those optimal parameters and even do optimization studies in anybody to find those parameters, those key parameters for your exoskeletons. On the other hand, if you have developed your exoskeleton already, you can evaluate your exoskeletons. You can analyze the effect of the exoskeleton on the human being. So how will the joint loads change from before, also from a human without an exoskeleton to a human wearing this exoskeleton? How will the muscle activations change? And in an anybody simulation, it's very easy to simulate an injured or injured muscle or not functional muscle. So you can also simulate patients with the anybody modeling system. And you see, especially in the rehab process, you can evaluate how will this exoskeleton help during this rehabilitation process of the patient while he wears an exoskeleton. So I have prepared a couple of models from literature to show some examples of what has been done in the past. So the first model is, first paper I'm showing here is from Xu et al. From 2012. So they developed an assistive shoulder orthosis for brachial plexus injury. So on the left side here you see this device. It's a wearable device, spring-loaded with and cable-driven. So it has adjustable preloads in these cables. And they simulated a motion resembling picking up a phone, duration of 4.6 seconds. And these brachial plexus injuries are seen that in this neck region that you see here on the right side, several nerves are damaged or are not working completely. So I'm not going into the very details of this model, but all I wanted to show now is that they have shown, so they have optimized their device using the anybody modeling system, and then they could see basically as a final goal. So the blue curve here is before the optimization, so basically the human without a functional exoskeleton. That has very high, so you see here the maximum muscle activation in this upper extremity, and you can see that it has been reduced to a fraction of this initial part with this optimization done on their device. Another example is from Agarwal et al. So they also looked at upper extremities, so they had a very basic exoskeleton for the elbow joint, and they looked at different actuator moments and their effect on individual muscles. So they took a standard control, so that is just a human without any exoskeletons, and looked at the muscle activations to lift a dumbbell. This is here the upper graph, and then they looked at the same motion with an exoskeleton, and they had their different moments in there, and a constant assistive moment, a variable assistive moment, and another assistive moment inside this exoskeleton. And I'm only showing here the variable assistive moment. And when you look here at the graph, you see again that here we see muscle forces for those individual muscles. They are reduced again to a fraction of their initial values. A third example that I have here is in a very different area. So Alray and Fatala developed a weight transfer device. You see that here, a picture on the right side, and also in the simulation on the left side. This is a device with a passive stiffness in this device. So it's not an active exoskeleton, it's a passive one. And it helps for workers that have to work a lot in a stooped posture. You see that here on the right side again. So if you have to carry heavy weights in a stooped posture, it will affect, of course, your back, especially in the lumbar spine. So we will have very high loads in there. And they designed this weight transfer device to lower the loads in the lumbar spine. And therefore, they looked at forces, compression and shear forces in the lumbar spine, so between the L5 vertebra and sacrum. And here in the graph you see the forces. The first three lines here show the compression forces for no weight, a weight of 4.54 kilogram and 9 kilogram. And then you see the empty bar, which is no device, and then the lower force. So with these checked bars in there, you see they could simulate that there is a reduced compressive force in between the L5 vertebra and sacrum. And also the shear forces that are the next three columns in this graph could show that with the device they have lower force in this joint. So a more complex exoskeleton was developed and then also used in a simulation by Zhou et al. And they designed this exoskeleton for industrial workers who have to carry heavy loads during their work process. And they had the research question in there: how do you have to attach an exoskeleton to the human? What is the optimal way? And they did various simulations in there. And on the left side you see here also recordings with motion capture of a subject carrying some loads in there. And then they have done those simulations in anybody, and their conclusion was if you don't have high loads or don't carry high loads, the effect of how the exoskeleton is constrained to the human is not very important. However, if there are high loads, it's better if there's a tight connection between human and exoskeleton. So this is just a short overview of what models are out there. There are actually a lot more models out there, and if you go or papers out there, if you go to our homepage on anybodytech.com, there's a full list of publications, and you will find a lot more there, publications in relation to exoskeletons. So now let's look at a different example. So this is now a little example my colleague Moonki prepared for us. So let's say I have designed an exoskeleton and want to know how will it affect a human subject. So how will we proceed in this case? So first of all, we have designed a little exoskeleton in SolidWorks. So we will use the SolidWorks to Anybody interface to import it into the Anybody modeling system. So geometries, inertia, joint locations, dimensions, everything's reference nodes will be automatically brought into the Anybody modeling system. So in the Anybody modeling system, we define now what actuators will be in the exoskeletons. So we have 6 joints in our exoskeleton, so we have 6 actuators in there. So 2 in the hip on each side, 1, 2 in the knee, and 2 in the ankle. So in our case, we didn't know exactly what is the perfect actuator, so we developed 2 different models. So one has a very strong actuator in each joint, and the other one only with a medium strength. So neglect for now absolute numbers. Let's just focus on a strong actuator and a medium actuator. So in order to how to attach the exoskeleton to the human, so in our case it was attached in pelvis, both thighs and both shanks. and we fixed in there kinematically with that those were fixed, and kinetically, I hope I get it correct now. So the weight of the exoskeleton was carried by the exoskeleton itself, but all other forces were basically then attached to the human. So let's go on for now. So what have we done then as a motion? So in our case, we wanted to see a sit to stand motion, and here I have two animations. So the motion was exactly the same for both cases, and in both cases we predicted the ground reaction forces ourselves. So you see here our standard guy, so our control guy moving, and now the subject with the exoskeleton moving. So the motion is exactly the same. The predicted ground reaction forces are of course different, because on the right guy with the exoskeleton, he has a higher weight, so the predicted ground reaction forces will change. What you don't have to worry about that, the Anybody modeling system will do that for you, so no need to do any special computations there. So now let's look at some of the results. So first let's focus on the human being. So we look here at the hip flexion moment. So what has the human being to produce for torque in this case? So we look here first at the red line. So we see the human itself, so without the exoskeleton, has a torque between 45 and then going almost to 0 in the hip to do the sit to stand motion. So if we add the exoskeleton with this medium strength, this is this gray line in the middle, it starts at 30, so we have a decrease there of more than 15 Newton meters, and it goes also down almost to 0. And if we take then our other exoskeleton, the one with with strong actuators in there, so it's a lot more reduced. So we are at 10 Newton meters over the 2 seconds of these sit to stand motion. This can be seen also when we look at the joint reaction forces in the hip of our human subject. So the human itself is again the red line. He has at the beginning almost 2.5 times body weight, maybe even a little bit more. And that's reduced to the end while he's standing straight up. However, with the exoskeleton, so even with this additional weight of the exoskeleton, we have a reduction of those hip joint reaction forces to about 1,000 Newton, and then when we use this exoskeleton with strong actuators, we have even less forces in there. So the same can be done now for the knee joint. So let's look at the knee flexion moment. So this is again the moment that the human being is producing during this sit to stand motion. And we see that the human here has a very high knee flexion moment of roughly 70 Newton meters starting and then reducing over time. However, when we introduce our exoskeletons, we see again we have a significantly lower flexion moment in both cases, while the strong actuator, our exoskeleton with a strong actuator, has no more flexion moment. So everything in there is carried by the exoskeleton in our case. This can be seen also again in the knee reaction forces. We see again high forces if we have a human alone, and reduced with our exoskeletons. So the medium actuator has a reduction of a max of maybe 1,000 newtons, while the strong actuator has then a knee reaction force in the human of maybe something in the area of 200 newtons. So it's very low loads in this human being while using or while wearing this exoskeleton. Now let's look at the exoskeleton itself. So let's go away from the human and go to the exoskeleton. So here we see some results in the exoskeleton. So here we only have two graphs. So one is the medium, red is the medium, and gray is the strong actuator in the exoskeletons. And on the left side here we look at the hip actuator moment. so the torque in the hip, and on the right side it's the same for the knee. So we see that the medium produces a lower torque compared to the strong actuator. You see also here in which range are we, in which area are we. So you could also turn around the game now and see if I want to develop exoskeletons, what torques do I need? Can I provide engines or the actuators that can provide those torques? How big have they to be? Especially when you look here at the knee actuator moment, it's a very high torque that has to be produced by this actuator. So the same can be done, of course, and anybody can compute a lot more variables. So we can do the same also for power. So which power? Here we have again, so the red line is the medium, gray is the strong actuator. So we have the power shown here for hip on the left side and knee on the right side. So you will see also what power is needed, so in watts here for my actuators. So I'm already at the end of my presentation, so that's just a little, you can call it a little teaser, so a lot more is of course possible. So I wanted to show you today only how can you use a musculoskeletal simulation with anybody for when you develop exoskeleton. So basically, again, there are these two ways. So you can develop exoskeleton, so you can optimize key parameters with anybody, like torque, like power, so those last graphs that you have seen. On the other hand, you can also evaluate what is your exoskeleton actually doing on your human. In our case, it was a healthy subject, but if you have a patient, you can do that as well. So how will the patient or the subject be affected by these exoskeletons? Then in our case, we used a fairly basic way to attach the human or attach the exoskeleton to the human body. There are many different ways, so from really rigid connections to just connect some degrees of freedom, having some carried by the human, having some carried by the exoskeletons. We also have done some elastic springs or elastic elements using our functionality that we call force-dependent kinematics. So that was way too complex and too much to show it in here, but maybe we'll do it in another webcast in the future. So you see, today that was more just a general overview and a teaser of what is possible, but in general there's a lot more possible. So you can look what we haven't shown here. It's simulate muscles as well, activations. I also didn't show now we can calculate metabolic power or mechanical power in here. So as I said, there's a lot more possible. Maybe stay tuned in and we will keep you up to date what else is there in the near future. So for now, you can still enter questions if you have them into this box, the Q&A panel. If you have any questions later on, feel free to email me at aa@anybodytech or Moonki, our exoskeleton expert, on mj@anybodytech.com. There's also the chance to meet us in person. So in the next weeks at pre-RS, ORS, there will be some of us in New Orleans. There will be in April, there will be anybody intro event in Germany, in Regensburg, where I will be present, and there will be another webcast focusing on the lumbar spine in April as well. On the other hand, like, we are always online available, so if you go to our homepage, you will see all the events at anybodytech.com. You will see also dates where we are, and I mentioned before there's a publication list out there where you find many publications. We have our community homepage, ndyscript.com, with a wiki and a forum where you can ask questions as well. And finally, we also have this YouTube channel at youtube.com/anybodytech, where many videos, help, demos, tips and tricks are shown in short little animations, and also this webcast will be uploaded there in the next days. So if you missed something, if you tuned in a little bit late, you can join us or see the webcast in there again. So I will talk to my colleagues now. If there are any open questions, please give me a minute to do that, and then I will see if I can answer anything live for you. So there was one question in the audience. What are the benefits of a predicted versus a measured ground reaction force in your example? So the benefits are you don't have to measure the ground reaction forces, especially in many cases you can do a simulation before making a real prototype of an exoskeleton. So just reducing costs, reducing time in making just a CAD model, a CAD design, and test that in a simulation. And therefore you cannot record or you cannot measure the ground reaction forces. So you can then use this function in anybody to predict the ground reaction forces. And that will make it a lot easier and quicker in your development process of the exoskeletons. If you have, of course, the exoskeleton already and then have the measured ground reaction forces, you can use them, of course, as well. But on the other hand, like even if you want to do slight changes in an exoskeleton, it can go a lot quicker without any measurements itself.